Welcome. The session here is Databases the Primary You Never Had. I hope that's what you're here for. I am Isaac Cunin. I am a senior project manager with Tableau. I work in our back-end data space. And actually, if you heard about Project Maestro, that's my big thing right now. I like that. I like that. So, we'd like to hear from you more. The agenda for today is to demystify a lot of the database terms and concepts that you hopefully have had some exposure to, but maybe you don't know a lot about. We're just talking a little bit. The leveling of this talk is an interesting one, because we've got a very diverse set of people here. And so if you know databases in and out already, this talk is going to be way under-leveled for you. And if you really don't know a thing about databases, this might be a bit of a stretch for you. And I would, by the way, love feedback. This is the first time we've given this talk, and trying to figure that out is hard. And so I'd love feedback on, oh, how was the level? Did it work for you? But we're going to try and demystify a bunch of basics about databases. I want to connect Tableau to that database a bit for you, help you understand how Tableau actually interacts with that underlying system. The focus in this talk is going to be on what we call relational databases, and I'll explain a bit more about what that means. These really are sort of the bread and butter of the database world. So there are a lot of non-relational systems out there these days. They're proliferating. But most of them borrow some concepts from these systems. And these are really a very common thing that you'll probably run into if you haven't already. OK? So let's get started. What is a database, or what is a database management system? And you'll often see the acronym a DBMS. OK? It is a piece of software that helps you store and query data efficiently. And I want to break this up a little bit. So it is a system. It's software. All right, hopefully that's not a surprise to anybody. It's for dealing with data. Now this one starts to get interesting. So what data do they deal with? How is that data formed? How is it formatted? How do you interact with it? How is it structured? We're going to talk a bit about that today. Querying. So querying is how database people say, ask a question, or how you interact with the system. So how do I interact with that system to get my data out? Efficiently. How do I make this whole thing fast? The database is of no use to me if it's in there, my data is in there, and I can't get it out in a reasonable time frame. And then how do I keep them safe? So the storage of it, a lot of that has to do with keeping data safe. The meat of this talk is going to be on those three middle parts of it. So how are the data structured? How do I query them? How do I do it efficiently? We might have a little, if we have a little extra time, we'll talk a bit about the last one. The first one I hope everyone gets. OK? So let's start. What data and how are they structured? And I'm going to use a motivating example. I got this from my wife. So my son's now in first grade. My wife's involved in the PTA, and she's doing event coordination. And as she worked through this, I found myself giggling. Right? All these problems that she was having are just standard database problems. And it turns out it makes a pretty good introductory example that should be fairly familiar. But it's real. I've changed the names. But the problem is a real one. So the PTA wants to collect information on parents and what kind of events they're willing to help out with. OK? They want to use this so they can help organize and get volunteers for events. And so they have the parents fill out a questionnaire. And they get back some data. What kind of data might they get back? Well, they get the name. That's great. That identifies the parent. They get a phone number. They need to be able to contact the parent. They, of course, want to know whether they're a PTA member or not, so they can decide whether to hit them up for 20 bucks. And then, what events are they willing to help out with? So here we've got a bake sale, a movie night, field trips. So they have a questionnaire they fill out, and they dump it into a table. Right? This looks a lot like a spreadsheet in Excel. And now I could start to ask some simple questions. So for example, how many parents are willing to help with the bake sale? And you can just look at the data, and you can see, well, there's 1, 2, 3. You could find those 3 parents. And if this was in Excel, I could just go to that header up here, and I could filter on bake sale equals true, and I'd get a list of the parents that are of interest to me. So this is a spreadsheet. How many of you are familiar with spreadsheets? I thought about asking the opposite question, but I think that one poor guy back there it seems unfair. OK, so I want to show you the spreadsheet. Here it is. There it is in Excel, glorious Excel. Everyone knows Excel, right? And so if I wanted to filter on this, I could just filter on this. How do you think I got that table in the PowerPoint? I started here. I just put it in the PowerPoint. So when we talk about the relational model, the core concept is the table. And the right way to think of a table is it's sort of a nicely formatted spreadsheet, like what we have here. Now, this is Excel. I can put data anywhere I want. I can fill out some cell down here with some random garbage if I would like. That's fine. It's not fine as a relational table. So a table is nicely structured. It has a header, right? We'll talk about this. This is the schema for the table, the name, the phone number, et cetera. And also the types for those. Excel is a bit loosey-goosey with types. Databases are not so loosey-goosey with types. And then a set of rows that match exactly what that header shows. Okay? So that's the basic concept in a relational database. And in fact, I can come over to SQL Server here. So SQL Server is a very common relational database. It's one of many very common relational databases. I'm going to use it because I worked on the SQL Server team for a long time, and I'm very comfortable with it. If you have access to SQL Server, you can use this to recreate all of these demos. If you have Oracle or DB2 or MySQL or Postgres or yada, 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 they all basically, for everything we do today, they're going to work exactly the same way. They'll have somewhat different tooling. This is a program called SQL Server Management Studio. If you go get SQL Server Express, it will come with this. But Postgres has their tools, and MySQL has their tools. Everybody has their tools. They're just slightly different. So I can look at that data here as well, and it will look very familiar. Now, let me actually execute that. We'll come back to what I just did, but you can see that the data that it returns is really exactly the same as that spreadsheet we just saw. So what I have in the relational database really is, at its core, just another form, another place to store that table that we saw in Excel. So those nicely structured Excel tables are really the right concept to start to move into that relational database world. OK? All right, let's try and make this a bit more interesting. Let's start adding some more information. So in particular, let's expand our question a little bit. How many fourth grade parents are willing to help with the bake sale? I need more data. In particular, I need child information. I don't have any information on where their kids are. I need to add that. So here's some child information. I've got the child names, I've got their grade, I've got their class. I need to somehow put this together with the parent information, because I need information on the parents and what they're willing to help with, and I need information on the children and what grade they're in. So how do I put this together? So in Excel, if I were to do this, I'd probably squish them all together into a nice big table. Right? Excel doesn't deal well with multiple tables. I can do VLOOKUPs and all sorts of stuff like this, but that becomes very awkward very quickly. So the first sort of impulse that most people would have with a spreadsheet is, all right, let me just stuff it all together. And I'd end up with a table like this. Right? So I have the parent name. Here's Marge Simpson and her number and all of that information about her, and then her child, Bart, and his information. And we just put those together. That's perfect. And, well, wait, here's Marge again, and here's her phone number again, and all the same information, and then Lisa. OK? Now, that's not bad, right? Except, well, all right. This does make it hard to manage. How did I get this information? The parent came and they typed in a form, and we recorded a row. Do we make Marge fill out 2 forms? That's kind of unfortunate. Maybe we could just have her fill this out once and then duplicate it once for each child and put it in here. And then she comes back and she says, well, Maggie's entering school, and I need to fill out another form, and my phone number's changed, so I changed my phone number. Which one do I change? Do I change them all? What happens if Marge has a different phone number in our database for Bart and for Lisa? Or if she answers differently for these questions for each row? We've got to keep them in sync. This is what database people call denormalized, and database people hate denormalization. We'll talk a bit more about this. But really, it says there's a lot of redundancy in the data. it makes it very hard to manage. It also is going to throw off our counts. Now, we're going to see we're going to have problems with counts anyway. But if I want to do that count, if I say how many people are willing to help with a bake sale, well, I get 1, 2, 3, 4, 4, right? But that's wrong, because Marge just got double counted. She can only help once. OK. We could also try and stuff it into a table like this. We could say, all right, we're going to have 1 row per parent. And then when we get over to the children, we'll just have a comma-separated entry. So we'll have Bart and Lisa, and we'll have 4 and 2, and we'll have Krabappel and Hoover. And now, well, look, this breaks uniformity. Some entries have 1, some entries have 2. Sometimes I have to look at the entry. Sometimes I have to search within the entry. How do I do a filter for this in Excel? If I want to know who's in grade 4, I have to have a drop-down. I have to say, well, if it's 4, or if it's 2, 4, if it's 4, 2. And then we've got all the other grades, right? So this becomes a real pain to deal with. So the problem at the root is that Excel does have multiple sheets, but they don't work well together. You can do VLOOKUPs, but really this becomes very awkward very quickly. Databases, on the other hand, are built at their core to deal with multiple tables in a very seamless way. And we're going to see how this works as we go forward. So they've got a query language that lets you put this back together. You factor data out so it's normalized. Again, that really just means helping to eliminate these redundancies. And then you put them back together as you need them. A little terminology. So I mentioned the word schema already. This is just the structure of the table or the tables. So if I say the schema of this table is name, phone number, are they a PTA member, right? I'm just saying what each row would look like in that table. The children table will have a different schema. Schema is a bit overloaded. Some database systems like SQL Server use this to refer to a collection of tables. We're not going to use that terminology here. So here when I talk about a schema, I just mean the structure of the table or the tables. And another concept that's going to become very important is the notion of a key. So a key is just something that uniquely identifies the row. Think of it as a short name for the row. It's just some data in that table. So this could be, in our case, the names. Make good keys. It might be social security numbers. It might be some other identifier, right? It's entirely dependent on the data you're storing. Here we're going to use names. So in a database, I'm not going to try and do this squish of tables together. I'm going to actually just store 2 tables. Okay? So I've got the parent table. This parent table is exactly like what you just saw, right? And I have a child table. Now you'll notice that the child table is almost what we just saw, but I've augmented it a little bit. I need to know how to put it together with the parent table, and that wasn't obvious from the data. So I've added a key column. It's what we call a foreign key. So that parent name field that I've added refers to the parent table and the key in that table. So this is sort of the linking field you can think of that tells me how I connect these 2 tables together, right? Bart's parent is Marge. Marge shows up in the parent table. Okay? And we're going to use that. We're going to use that quite extensively. So this is the basic relational structure. I have a set of tables. They have a very rigid schema. All of the rows in a table conform to that schema, but different tables can have different schemas. And I can have many of them, and I can put them together with my queries. Okay? So let's dig into the query side of this. How do I get my data? All right. Let's back off and just categorize a few simple questions that I might want to answer. So the first one, what we call filter queries, are I've got some data. I want to squish them down. I want to remove ones that don't match some conditions. So I want to know which parents are willing to help with a bake sale. Very simple condition. Remove the rows where that's not true. What children are in grade 4? Again, just remove the rows where that's not true. We'll also do calculations. Sometimes we call these projects. Right? What is the length of each child's name? The data I've used doesn't actually lend itself to many very nice calculations, so I've resorted to something a little bit hokey. I'm not sure why I'd care about the length of each child's name, but we can do it. We will do it. Okay? So let's put these together and ask a fairly basic question, right? What is the length of each child's name in grade 4? And how would we ask that question of a database? Okay? So the basic structure of the simplest SQL query. So SQL is what's called the structured query language. It's very standard. It's been around for ages. It's a horrible, horrible, horrible thing, but it's very powerful. Okay? So the basic structure of a SQL query has a from clause, a where clause, and a select clause. The from clause tells me what table I want to pull data from. It may be more than one table. In this case, it's the child table. I say from child. The where clause tells me what condition I want to hold for each row. So in this case, it is I want grade to equal 4. And then the select clause, I name the columns that I want pulled out of the data, and I can also put calculations in that to create new columns. So in this case, I'm going to say name. I want the name column. And I'm going to say the length of the name as length. So this just says compute the length of the name and call that column length. OK? I could get them all if I want. I could put select star. You often see that. Select star just means all the columns. All right. Does anyone here know SQL? OK, what's wrong with this?
Wrong order.
It's totally the wrong order. See, in SQL, I told you it was a horrible language. You write it like this. It makes absolutely no sense, right? Most of the time when you sit down to write something like this, the first question you're going to ask is, where is my data? What table is it in? And so you answer that from question first. And then you say, well, all right, what of those rows do I want? And you put in that where clause. And then you say, well, what of that table do I really care about? And you fill out the select clause. But like I said, SQL is a horrible, horrible language. But it's very powerful. And it's what we have. It is very standard. OK? So yeah, if that's weird, it's weird. It just is. It's one of these things. It just is. OK, so let's move on to something a bit more complicated. We had multiple tables. We had a parent table and a child table. And I want to ask a question that uses both of them. That was the whole point of having multiple tables. So let's find out which parents have children in grade 4. All right, how do I do this? Here's the SQL for it. Let me walk you through the SQL for it. So the first thing is we have this from clause. And you'll notice that the select and the where clause are, if you fully absorb the previous example, they should now be fairly straightforward. But that from clause is definitely more complicated. In particular, it has this thing. It says join. And then it has this thing that says on, and then this condition here. So what this says is it says, hey, I want you to join these two tables, parent and child. So you've got the parent table and the child table. I've named both of them. And then I've got a condition. I want this column here, the name column in the parent table, to equal the parent name in the child table. So I've identified these two columns. And I said they should be equal. And what we're doing is we're saying, hey, all those pairs, are those matched? I want you to find all of those matches. And I want you, in your computer memory, in your computer mind, if it has such a thing, I want you to create an intermediate table that just takes all of the rows that match up like this and squish them together in one big row. Okay? So those two matches that I've just found are going to get squished together into these two rows. Right? There's all of Marge's information, and there's all of Bart's information. And then there's all of Marge's information again. And then all of Lisa's information. Now, keep in mind, this table that I'm showing you will never actually exist. This is just an intermediate product. So there's never any question of, hey, are Marge's entries out of sync? Because they were just created on the fly. There's no actual duplication of the system, which is good. We like that. But conceptually, this is what happens in the middle. So I do that for all of the matches, and I get this table. And then I go on to the where clause, and I say, where grade equals 4. And now I just identify all those rows where grade is equal to 4. There they are. And I'm going to remove the other ones. So that's the next step. And then I'm going to do the select clause. What do I want? I just want that first column. I just want the name. And so I will identify that and cut everything else out. OK? So there's the answer to our question, which parents have children in grade 4? Do you notice the duplication? Right. That's unfortunate, right? That's exactly the same kind of duplication that I might get if I'd done this in Excel. Now, I could say select distinct. I can put a keyword in there, select distinct, and then it'll only give me the distinct rows. All right? But we do have to, just because we've split the data out doesn't mean we can ignore duplicates. And we'll see more duplicates as we go. All right. The next step up in complexity, grouping and aggregation. And this I want to get to. I wanted to get to grouping and aggregation because this really is the core of what Tableau does. Tableau does all sorts of cool things with data, filtering and predictive, analytics of various sorts and whatnot. But the core of it is I drag things into my columns and rows, and we group data and we aggregate data. Okay? And then we visualize it. I don't want to diminish the visualization. That's obviously very important. But from the data side of things, grouping and aggregation, that's really what it's all about. So how many parents in each grade will help with movie night? And I can write that in SQL. It's getting a little complicated, but don't panic. We'll walk through it. Here we are. Now, first off, that from clause should look really familiar. It's exactly the from clause we just saw. So I'm just making it a little more complicated, but we're building on what you know. The where clause should look totally familiar as well. And we'll talk about the group by and what we've done in select. All right, so that middle part, like I said, very comfortable. We're going to create that intermediate table by matching up all the children and parents. We're going to filter out all the ones where movie night was false, keeping only the movie night equals true, and we're left with this state of affairs. Now, the next thing here is I say, well, I'm going to start grouping. And you'll see that the grade column here shows up in the group by clause, and it shows up in the select clause. This tells us how to break up the table. We're going to group it into sets of rows, and we're going to group it into sets of rows where that grade is the same. So we've got a group here of 4s, and we've got a group here of 2s. The group there of 2s is a group of 1, right? This is what we call a dimension in Tableau. And if you remember only one thing from this talk, remember this. This is what a dimension is. We tend to give all sorts of heuristics about what's a dimension versus a measure. But really, this is it. It is the set of things that define what buckets to create. In this case, it's just grade. I'm going to create 2 buckets, a 4 bucket and a 2 bucket. All right? That is a dimension. Now, there's more in that select clause. In particular, I have a count, and you'll notice the distinct. Again, SQL is a horrible language. That's how you write count distinct in SQL. It's very bizarre. All right? That's an aggregate. That's a measure. So that select clause has 2 kinds of things in it. It has a set of columns that show up in the group by clause, and it has a set of things that are aggregated. Right? So here, grade shows up in the group by, name is aggregated. If I put something else there, if I just put phone number there, for example, SQL will puke. Say, no, I can't do that. And of course, this makes some sense. The for group has multiple phone numbers. But I'm going to return 1 row for that for group. What do I return for that? I've either got to break that group up, and that would mean putting the phone number in the group by clause, or I've got to somehow aggregate those phone numbers together, maybe take the maximum one or something. Right? That's measures, and that's dimensions. Dimensions are what you break into groups on. Measures are the set of things you're aggregating on. Nothing else is allowed. Okay? So how does this work? What would you anticipate the result of this is going to be? How many rows are we going to get? 2 rows, right? 1 for 2 and 1 for 4. And how many values in the 2 row? How many in our count? 1. And how many in the other count, the count for 4? 3. You might think 4, but remember, Marge is duplicated, or sorry, Jerry here is duplicated. And we said count distinct. So we'll get 3. So that's what we expect. Now, I'm going to prove it to you. All right. So we're going to go back to SQL here. So this is the data, and I'm going to run. This is exactly the query that we just had on the screen. And I'm going to run that, and I'm going to get this value. I'm going to get this result. I get a 2. The count is 1. I get a 4. The count is 3. Actually, you'll notice that I didn't quite write the query that I did before. You notice I put this in here. I gave it a name. That's why it's called count. Right? Now, I also want to show you how this works in Tableau. All right, so I said this is what Tableau does. Let's see it in Tableau. So here's Tableau. All right, I'm going to connect to my SQL Server instance. It's just here on my laptop. I'm going to pull up my demo database, and you'll see it has exactly those two tables. I'm going to drag them in. I'll just double-click to bring them in. And we join them up. Children join to parents, and I say update now, and I get no rows. Anyone want to hazard a guess what happened? Wrong join clause, right? So we made a guess at what that join should be, and we guessed wrong. In particular, we made a perfectly sensible guess that the name of the child should equal the name of the parent, but of course that's wrong, right? We need to correct that to parent name. And now when I update the data, I will get exactly the table that I expected. So what Tableau is doing is materializing that internal table. And really, everything past this data pane in Tableau, well, I guess if we ignore blending, everything other than blending past Tableau basically works on a single table. One big fat table. So now I'm going to go to a sheet. And let's see, what did we say? It was movie night. Let's drag movie night into filters and say true. OK? And then let's see, we wanted the grade. And we'll put that in here. And we wanted the parent name. Here's the name of the parent. And we'll put that on columns. And I get garbage. What happened? Pardon? Hang on a second. I said dimensions and measures are important, right? So we use some heuristics to try and figure out whether you meant to group by something or aggregate it. And they're pretty sensible. Numbers, I'm going to aggregate. Those are measures. And strings, I'm going to break things up on strings, and those are going to be dimensions. But that's exactly wrong in this case. So I'm going to fix this. I come in here, I say, actually, you know what? I want to count distinct the names, and I wanted to use that as a dimension. And of course, a line chart is not really the best choice here. So here we go. Now I get my count. 1 parent for grade 2, 2 parents for grade 3 parents for grade 4. All right. Let's dig into exactly what's going on. So the easiest way to see what queries are actually being issued are to start the performance recorder, which is going to start recording the things that are going on. Now I have to force that query to happen again. So I'm just going to come over and refresh the data source, which is going to cause all of that query to reissue. And then I'm going to go stop the performance recorder. And it'll churn for a bit as it builds the report. And this is going to come up. And once it does, I get a nice worksheet that has nothing in it. Now, there's nothing in it because my data is so small and those queries execute so quickly that it's filtered them out. So I'm just going to take this time and drop it down to 0. And now what I see is I get a few events, but in particular, I get this one query. And if I look at the query that was issued, it should look pretty familiar. There's a bunch of goo around it, all these square brackets. Those sort of help protect the names. They're not keywords in SQL if they're wrapped up this way. What did I select out? I selected a child as grade, sorry, the grade as grade, and the count. And here they're using count big. That just uses a larger integer. It's the same thing as our count. Count distinct of name from child, join, parent, on, parent name equals the parent's name. That's exactly the query we had, the filter. Right? It's decorated a little bit more to make sure that it's run safely, right? But it's exactly the query we ran. And so this is what Tableau is doing. I put my things into shells. I tell it what are my dimensions or measures, which tells me what to group on, what to aggregate on. And then Tableau under the covers is generating that SQL query, sending it off to the database, getting back the results, and then putting a nice visualization on top of it. OK? So back to the presentation. How do I make it fast? That's our last topic. Indexes. It's always about indexes. If you talk to a database person, it's about perf. First thing, indexes. So the first thing to understand is that everything we have talked about so far is what we call the relational structure. Sorry, the logical structure of the database. What tables do I have? What are the types? This is all what we call logical structure. And there's another layer to this, which is the physical structure, or the physical model, which lays out how are these things actually represented on disk? Because these are all stored on disk. They're all squeezed into pages on a disk and written out somewhere. Now, that physical structure has an amazing amount to do with the performance of queries. And the beauty of the relational model, or one of the big advances in the relational model, is that they tease these things largely apart. So I can change the physical layout without changing that logical model. And I can tune the performance without changing the programs effectively that I'm running against my data. And we'll see this. So first, to introduce the notion of indexes a little bit more, I'm going to need a volunteer to help me with a bit of a demo. Can I get a volunteer? Somebody volunteer. Yes, please. Thank you. Otherwise, I have to volunteer somebody. Come on up. Thank you. What's your name?
Jennifer.
Jennifer. All right. Jennifer, are you familiar with the use of a dictionary? Well enough. All right. So here I have Merriam-Webster's Collegiate Dictionary, 10th edition. It's a little old. I'm going to give you this book. Now, that book, I'm going to ask you a few questions that I want you to answer with that book. I will tell you up front that all of the information you need to answer these questions is in this book. We're going to time you. OK, ready? Don't worry, they don't bite. All right, first question. What is the first word that starts with the letters R-O? Roach. Very good. That was very quick. That was very quick. I'd say maybe 15 seconds. That was very good. OK, now, here's the next one. What is the longest synonym for data? Why not? By the way, there's no thesaurus in there. What's wrong?
It doesn't do synonyms.
But the data's in there. You can.
It's true, but it doesn't help me find the longest one.
Why not? It's in there.
It's not categorized by.
It's not. All right. Thank you. All right. I think we've made the point. Thank you very much, Jennifer. OK. Now, all right, let's dig into this a little bit more. All right, so the dictionary. Here is an example of the dictionary. This is the entry that Jennifer found. This is not the definition of roach that I expect. I think it's chronological. I think that definition shows up a bit further down. We can talk about the schema of the dictionary. I say roughly because the dictionary, of course, is not quite a pure relational structure. Right? The definitions don't quite follow a very uniform pattern. But they're close, right? They have the word. They have the pronunciation. They have the word forms, like roach and roaches. They have the etymology, right? This comes from Middle English, from Middle French, right? The definition. All right, so the first thing to observe is that this clearly has the information in it needed to answer both questions. Right? So Jennifer was able to very quickly find the answer to the first question, right? What starts with RO? The information is there to answer the second question, but one of these questions is so much harder to answer than the other. And why is that? And of course, the answer is all about the index. OK, so a few concepts about indexes. We tend to break indexes into two types. I'm getting ahead of myself. It is its structure, right? An index is a data structure that's built to help speed up some set of queries, right? Right, sometimes the data are stored in the index. We call that a primary index, right? The structure itself contains all of the data for the table. Sometimes we build it on the side. We say, here's the data, here's another data structure on the side, and we'll call that a secondary index. All right, so the first question is, what is the index for the dictionary? It's alphabetical. It's an alphabetical sorting by the word name. So we've indexed the word itself, right? Is it a primary index or a secondary index? It's a primary index, right? That is, this whole book is really one big index, and all the data is in that index. So can we think of, a secondary index that would speed up that slow query? Of course, I think we already mentioned it's a thesaurus. So I could have also brought along a thesaurus, and then Jennifer would be much happier with me. Is a thesaurus a secondary index? Yes, right? It doesn't contain all of the data needed it doesn't contain all the data we used for the word. In the case of our second query, we could have answered that query with the secondary index itself. We wouldn't have had to go back to the primary data source at all. And sometimes that's true. And sometimes that's true in database systems. I can answer the query just using the index. Sometimes I have to use the index and then go back to the primary data source to find more information. So if I wanted to know what's the etymology of the longest word that's a synonym for data, then I'd have to look it up in the thesaurus and then go back to the dictionary to get that etymology, because thesauruses, whatever, don't usually contain the etymologies. All right, so let's try and bring this back and understand, in the context of our children and parent data, how this might actually look in a computer. So we are going to start to build a data structure. The first thing is that databases store their data. Traditional relational databases store their data as rows. This is actually the information for each row. And they sort of squish them into disk pages. So disk pages, they vary. Call it 8K, 8 kilobytes. A little chunk stored on the disk somewhere. Contains a bunch of rows. So here I've augmented my children with a few extra ones. And of course, I ran out of Simpsons names. So let's accumulate a few more. So we start adding data, we get more disk pages, and then we need to figure out how to find those pages. Okay? So we do this by introducing new disk pages that have some structure that helps me find them. So in this case, this node says, hey, if it's less than Bart, I'm going to have a pointer. I'm going to have a reference to that disk page that has the data. And if it's between Bart and Lisa, here's a different reference, and et cetera. And as we accumulate more data, we're going to build up more of this structure. And of course, once we have those two intermediate ones, we need to have a root of this tree. So this is what a computer scientist would call a tree. It's laid out in disk blocks on that magnetic spinning thing. By the way, computer scientists sometimes put roots of trees on the left, often put them at the top, but almost never put them at the bottom. But that's what we call the root of the tree, right? And so how do I use this? Let's say I had a question. What's Elijah's grade? This is great. Here's the SQL query for it. Select grade from child where name equals Elijah. And yes, I can put it all in one row. That's fine. How do I do this? Well, all right, you're talking about the child table, great. And you're talking about the child name, great. I've indexed by child name. I'm going to walk the tree. I'm going to start at the root of the tree. I'm going to say, hey, Elijah's less than Ralph. So great, I'm going to follow this pointer to this node. I'm going to say, hey, Elijah's between Bart and Lisa. Let me follow the next pointer. And I end up at this node, this page on my disk. And now I can walk through that. I can say, well, no, it's not Bart. Yes. Oh, there's Elijah. Great. And there's the grade. Now I have to keep going. I have to look at the other records here, because there might be another Elijah. So I look at Greta, et cetera. So I'm done. So I get that one result. And I did a few disk reads. In this case, I did actually 3 disk reads to pull in those 3 pages. And that really is the predominant source of time in a traditional relational systems. How many times do you have to read in from disk? Because disks are slow. And they're just getting slower. You laugh. They are getting slower. Relative to everything else, they keep getting slower. Memory keeps getting faster. CPU keeps getting faster. But disks, they're getting faster, but not really very fast. So they keep getting slower relative to everything else. So the disk read time tends to predominate in these kinds of queries. Well, what if I did a different index, right? I could build a different index. By the way, this is a primary index, right? All of the data is actually stored in the index structure itself. This is, I should also mention before I go on that I've given a simplified tree. The actual kinds of trees that you'll see in real database systems are usually what's called a B+ tree. They are a very highly tuned data structure for these kinds of systems, right? For these relational database systems. They tend to be very broad, very wide, not very many levels deep, right? So they try and keep the depth of that tree, the number of reads I have to use to get to a record, very small. Let's say that I did something else. Let's say I indexed this by parent name. Well, what does that mean? It means, well, I'm just going to reorder all of those records. And I'm going to build a new tree on top of it that instead of having child names inside, has parent names inside. My query doesn't change. This query never mentioned the index whatsoever. And it doesn't change at all. And that is that logical physical split that we're talking about. The schema of the table is the same. I didn't have to do anything with my program, but I just did drastically change my performance characteristics, because now, how do I find the answer to this? I can't use the index. I'm looking at child name, but that's all parent names. I can't use it. The system won't use it. Instead, I have to look at the first name. I say, Allison, no. Eves, no. Ralph, no. And then I go through all of these, and eventually, after a while, I get to Elijah, and I can answer my question, right? But I'm not done, because there could be another Elijah, and it could be anywhere. So I have to keep going and going and going. I actually have to look at all of my data to be able to answer this question. So of course, this is small, but I've gone, even with this small example, from 3 disk reads to 8 disk reads. And as the data gets bigger, that disparity gets even larger. So the choice of index has a huge impact to the perf of certain queries. Now, if I ask a question about parent name, this is maybe the right structure. So you have to have some idea what questions you want to answer to pick the right indexes for your data. By the way, just terminology, we just did a scan. I scanned the data. The other, when I actually use the index and work in, we call that a seek. So you generally prefer seeks over scans because they're much faster. All right? Let's see, what time is it? All right, I've lost my clock here. So let's talk about the NoSQL. This is a bit of a coda. So we've talked here about relational systems. The idea behind NoSQL started out as, hey, these relational systems are horrible, and we don't want to use them anymore. It really meant no SQL, no relational systems. This has evolved to mean not only SQL, because there are limitations in any system, and it turns out that relational systems are actually useful for a lot of stuff. And it's unreasonable to replace them everywhere. So you can get a bit choosy now as these have proliferated. So those relational databases aren't going anywhere, but you might start to see other kinds of systems. So traditional relational systems, we've talked about a few of them: PostgreSQL, Oracle, DB2, Informix. There's a bunch of them. The language you interact with is SQL. This is very, very, very standardized these days, right? These are all, for most jobs, these are pretty interchangeable. Doesn't really matter too much. Another set of things that you will see are column stores. So the TDE, the Tableau data engine, if you create an extract, the thing that we use is a column store. Hyper is another column store. Things like MemSQL, HANA. I've also mentioned SQL Server and Oracle both have column stores as part of their systems. You can create a column store within Oracle and within SQL. DB2 may have one, I'm not actually sure. These still present that same relational model to the user. So they'll still run the same queries. They're just organized very differently. Instead of a row-oriented store like what we've talked about, they store each column separately. And this actually is really, really good for the kind of analytic questions that products like Tableau ask. Those grouping and those aggregation problems fly on these systems. They also fly because these column stores are often in memory, right? So Hyper is largely in memory. MemSQL is in memory, right? A lot of these systems work in memory, so you're not getting those disk reads. And so these have come along, and they have totally revolutionized the way that people structure data for these analytic workloads. They are not good for what we'd call OLTP or transactional workloads. If I'm running a point-of-sale system and I'm just collecting lots and lots of sales, with a relational system, you imagine, oh, I've got a table, and I start throwing rows into pages. They just stick them at the end. That's great. With this, I've got to hit each column with each value, and they tend to not do so well. So you have to understand why you pick one over the other, but the interaction with these things is the same. Key value stores or document stores, so things like Couchbase, MongoDB. These really are meant to, the access for them is in a lot of ways much simpler than what you get with SQL. They're not built to do joins and that kind of thing so well. But you can stuff documents like JSON documents in that have a much less rigid structure. And so they're very useful for that kind of thing. People like these things for logging often. Because if the structure of my log changes, I don't have to go and muck with the database. I can just stick it in there. Some of these have their own APIs or their own languages. Oftentimes, though, they expose a language that is a modified version of SQL. It would look like SQL to you, but it has other stuff in there to deal with the fact that the data is not quite so regular. Cubes are also a thing that you'll see. Now, these are actually fairly old, right? These column stores and key value stores are more of a recent invention than cubes. And in fact, column stores are by and large starting to steal or have been stealing workload from cubes. Cubes are an optimized structure for dealing with these grouping and aggregations, where they pre-aggregate and let you slice and dice. But they tend to be more rigid than what you can do with a column store. And so the column stores are coming and eating in very rapidly to that cube storage. And then there are other more sort of niche databases, time series databases or graph databases that are optimized for other workloads. These are a little less general purpose. All right? Now, how many minutes do I have? I've lost time. I have 15 minutes. All right, so I'm going to give you guys a bonus topic. So we talked about keeping the data safe. Now, if you hear a database person talk about ACID, they're not out to get high. All right? It really comes down to a method for keeping data safe that all of these relational systems that we've talked about implement. And so here's the thought experiment. I go into a bank, and I say, I want to move $100 from my savings account to my checking account. What do I need to do? Well, first off, the bank needs to check whether I've got $100 to move. Can I even do that? All right. Then they have to take $100 out of savings, and then they have to put the $100 into checking. Right. These are really 3 discrete actions that need to happen to do this successfully. And so what do I want to hold as I do this? So the first thing is I want it to be atomic. So that's the A in ACID. Okay? The move either happened or it didn't. In fact, all of those things either happened or they didn't. In particular, you could imagine that they remove $100 from my savings account and then stop. I'm not going to be very happy. They could also add $100 to the checking account and then stop. Now, I'm going to be pretty happy, but the bank's not going to be so happy, right? All of these things need to happen, or all of them need to not happen. And that's this atomicity, or we'd say the transaction has to be atomic. It needs to be consistent. So I've got this constraint. I have to have non-zero balances. I want that to hold. I don't want that to be violated. They have to be independent. So if my wife is making transactions as well, then they can't sort of in concert both be accepted and violate constraints, right? They have to each work. And then finally, it has to be durable. So once the bank tells me that the transaction is complete and the money's in checking, I've got to be, I guess that's too punny. I'll do it anyway. I have to be able to take that to the bank. It may not happen. They may try and do this, and it might fail, and then they'll tell me, hey, the transaction didn't happen. But once they tell me that that thing happened, it's done. And so this is ACID, atomic, consistent, independent, and durable. And this is also a thing that these NoSQL databases often tend to relax, because it turns out this can be very expensive to do, particularly in scaled-out systems. And so maybe I don't need this for everything, right? If I'm running a bank, I want this. I really want this. But if I'm Facebook and I post my status update and you don't see it right away because it hasn't propagated through the system, that's okay. Right? I don't care about sort of that same consistent view everybody having, right? All right, so that's ACID. All right, questions? Happy to take questions at this point. Yes?
How do you select an index if you want less granularity or more granularity?
So you're asking, how do you select an index? Are you asking, how do you decide what index to make? Or how does the system decide which index to use?
How do you decide which one to make?
Right. All right, so the question is, how do I decide which index to make? You have to have some idea what your query workload is. So Jim Gray, who, by the way, won the Turing Award basically for coming up with this, he had this game. He said he'll play 20 queries. Right? You give me your data, you give me the 20 queries you want to run, and I'll design you a database system. You have to have some idea what you're going to ask to really make the right index, or indexes, and you can have more than one. Usually you can have one primary index, as many secondary indexes as you want. There's usually a performance, there's sort of a performance tax to having additional indexes, because it is an additional data structure that needs to be maintained by the system as you make changes. It takes up space. So you don't want to index everything, usually. You'll often index keys, right? So I'm often joining on keys, or I'm linking based on keys, and so those indexes tend to help quite a bit. And beyond that, you really need to know what your query workload is, right? So it may be that the parent name for the child table is not a key for the child table, but if my queries are often asking about the parent's name, the index might help. But you have to think through what your query workload is on your data. It's also true that a bunch of these systems will have information. They will tell you, hey, if you had this index, I think the queries that you're running would be faster. And so those can sometimes give you hints. So in SQL Server, those are called the missing index views. And so you can sometimes use those once you have queries to help you figure these out. OK? Questions? Yes?
You said that this read is the slowest.
Yes. So the question is, I said that disk reads are the slowest, but if your data is on the cloud, isn't that connection going to be slow? It could be, right? So data movement in general is a very expensive thing. But you could imagine I run a query that touches a lot of disk, but returns a very small result. Then the disk reads are probably going to dominate. If my query is returning gobs and gobs of data, well, I have to touch the disks. I wanted the data. There's no out. Right? If I need to return all the data for a table, I have to touch all the data. Right? And then, yes, that transferring it over the internet might then be the dominant cost. Other questions? Yes? I can. I think I can. I can. That's all. All right. Other questions?
So I'm curious your thoughts. So I've tried to do like SQL. I've done like SQL trainings at my company and things like that. And one of the biggest mistakes I've seen people make, both with beginning SQL and with Tableau, is not understanding three-value logic. Could you go over three-value logic?
Yes.
That's very fundamental.
Right. So the question was, hey, what about three-valued logic? So it's true. So in databases, we have true, false, and then sort of undetermined. And so you have nulls. A common mistake people think is they think that null equals null. Right? Null in a database does not equal null. Because it's undefined. It's unknown. But what is unknown equals unknown? I don't know. Right? So it's maybe a bit much to go into right now, but do be aware that, yeah, the nulls have an interesting place in databases. And the way that they interact has very interesting ramifications. So yeah, if you want to know, for example, I want all the rows where a column is null, I can't say where column equals null. Because null equals null is undefined, and that's not true. And so it doesn't come through. They have a special predicate, is null. Where is null? So you have to be aware of this. I think anything deeper than that is probably not appropriate for here. Yes?
What are some best practices for like people who are on the BI side when they're working with the people who are actually managing their databases to make sure that all of like our needs might be addressed and that they have like enough background to be able to optimize it?
Right. So the question is, effectively, how do people on the BI side talk to people on the back end about improving some of these things? One of them is, yeah, share the workbooks. Share the queries that they're generating. Help them understand the kinds of workbooks that you want to put together. What do you view as a dimension versus a measure? Right? And work with them then. They'll have a much better picture of, yeah, How do I structure this? What indexes do I make? But yeah, you can grab the queries sometimes. That can be very helpful because the guys in the back end, they're going to know SQL, right? And that's often these guys just eat it up. So if you can work on that level, they may not know Tableau, but you show them that query and then I see what you're doing, right? Did you have a comment on that? Oh, let me go back here and then I'll come back to you. Yes.
I've heard the term partitioning.
Yes.
Is that just an aspect of indexing? Or?
Yeah, so the question is about partitioning is how does that relate? So with partitioning, often what you'll do is you'll take some, maybe the way to think about it, is in the index structure, you could imagine that subparts of that tree I'm going to put on different disks, or at least on different files. Different disks is often helpful, right? And different systems deal with these somewhat differently, right? In SQL Server, you can dynamically add more of these partitions and remove them, and it will do a very good job of not even hitting disks that aren't touched by a particular query. They don't even need to be present. You can do these very neat demos where I can unplug disks and still run the query because they will eliminate the need for those partitions that are residing on different hardware. This can definitely be a huge performance gain, particularly as data gets large. So yeah, but you need to think about how it's being partitioned. So is it being partitioned by date, and can I swap in new partitions as old dates become unimportant and new ones become more important? Do I fan these out based on some sort of ID? Right? How do I think about that? It's sort of a deep subject in and of itself. Here and then there. And then I think that's probably about all we have time for. I have 5. All right, cool.
Can you explain Hadoop in context?
Yeah, good question. All right, so can I explain Hadoop in the context of this? So Cassandra and Hive run on Hadoop. Hadoop is really a bunch of things. So Hadoop is a distributed file system. That's part of what it is. Hadoop is also this MapReduce layer that sits on top of this distributed file system. So it's a way of writing programs that can sort of scale out and move data between these nodes. What Cassandra and Hive do is they put effectively a database layer on top of these systems. So it's sort of a layer of abstraction above where you're not really dealing with raw Hadoop. You're dealing with something that looks like a database but is distributed underneath with Hadoop. But Hadoop is sort of a complicated thing. It's almost a distributed file system and a distributed operating system and this MapReduce logic and all these things that are built on top of all of that. So it's a bit of a complicated onion these days. Yes?
About a year ago, I inherited a whole bunch of reports that prior to me touching them, they're all in Excel.
Yep.
And the data was always just typed in, probably with like 2 fingers, and came from various different sources. And the very first thing I did is I just made this Excel file where each tab was like a table
Right.
that had the source data from each of these that I didn't touch. It was 100% pure. And I've gone back and tried to get like 5 years history on that. But of course, like one of the things that I report on is a location. And each of these has its own version of the name of each of these locations. Some of it's archaic, some of it's spelling, it's cats, all kinds of stuff. So I have this one table that has 13 data sources.
That's right.
It has 14 columns, one for each of the data sources, and then the one on the left is the one that I report on.
Right.
And then I just do a VLOOKUP. Every single time I do a report, I do a VLOOKUP, and then it's the number of spaces over to get to the one that applies to that table.
Right.
I want to migrate this into like a database. So should I rename all of those locations to the one true name?
But you then also need, sorry, so the question is you've got a bunch of reports that you inherited, not exactly the best kind of inheritance, I suppose, that you inherited, and they have somewhat different structure, and you want to figure out how to put them together.
Because he would just look at
Right.
it, he would see the archaic name, know what that is today, and type it in that cell.
Right.
I need to be able to look it up, so that's why I have like a VLOOKUP table,
Right.
essentially.
And so I don't have a great answer for you, except that I'd like to talk to you about Project Maestro. So yeah, this is a very common problem. So you're in the middle repeat. If you want to come back and see this again, feel free. I'll be over in the Four Seasons this afternoon. A few other sessions that might be of interest to you. There is the data blending session this afternoon, tomorrow morning. This is a longer sort of hands-on session. And there is, I guess the Conquering Cross Database Joins is happening at the same time as this. So you can look that one up online. So please fill out your surveys. I'd love to hear what you thought. Thanks for coming.